Okay, so in this part, I will make a tutorial on how to connect to the server with your account. So in the beginning, you open a remote desktop and you connect to the server. The IP is 140.112.175.226 and the port is 9999. And after you connect, you will use your ID and then log in. Okay, so after you log in the desktop, you will see there is a DDCC 1D and the DDCC 2D program. Okay, then if you double click the DDCC 1D program, then you will see the 1D simulation program will jump out. And this is the 1D simulation program interface. You can find there's usually you start a project from the architecture layer design, and then additional functions are in this part. So typically, you only need to work on this first interface to make like LED or quantum wave or MOSFET simulation. Okay, and if you click 2D, then you will see a very similar interface. The difference is that 2D you need to set up a region. So you need to set up material region and the material parameters, and you need to set up the mesh. Because 2D you need to fine-tune the final element mesh. So this 3 is equal to the 1D simulation program architecture layer. Okay, so this program is developed, the simulation code is developed in NTU, but the graphical interface is done in ITRI. There are several engineers to working on this project. Okay, and actually the interface was written by Poisson, so you can have some idea, and you can check the version that about this. You can find it's already developed for a long time. Okay, so if you have some problem to open this file, please let me know. Thank you. Okay, so I'm going to give a tutorial for the 1D. So the first structure we can try to test is like a LED structure. Okay, so this is a very typical LED structure, and we can start from this most simple one. For example, it's a P gain nitride. There's a 1 quantum wave, and this is N gain nitride. And this is a very simple 1D structure. Okay, so assume that we have this structure ready. So we open a 1D program. So in the beginning, we need to define the epi-layer. So everything starts from here is that first is always remember we need to define the project name. So if we define the project name for project test 1, okay, this is the first test project, and then we need to save as save. And save is very important because it decides where your data are saved to. So before you start this, you always remember that you need to set up in your desktop, okay, you can set up a project name. Okay, we say project test 1. And then we go into the project test 1, and we save the file called test 1. Okay, so that's the most important step. Then we can add epi-layer. So you can see there is an add layer interface. So first is that how many layers you are going to add. And this is the materials to choose. So you can find out many kinds of alloy you can choose. So in this case, it's indium gallium nitride. And if we go back, we can say they are gallium nitride, indium gallium nitride, gallium nitride. And of course, that gallium nitride can be calculated by indium gallium nitride. So we want to add first layer. Okay, we say the first layer is from the bottom. So sorry, it's from the top. So top, the first layer is the top layer. So the first layer is 100 nanometer, so we say it's 1000 angstrom, and the composition is 0, and the p-type, and the p-type doping, okay, we can say the doping density is 2e19. Okay, so we can say it's 2e19. And after this, we can apply. So you can find we had first layer is the gallium nitride. Then we can set up the second layer. It's still number of layer 1, and the thickness is 3 nanometer, so it's 30 angstrom. And that's like N-type, or we can say it's intrinsic doping. Okay, so we can say the doping density is 0. Okay, then we apply this, so we can get a gallium nitride layer. Okay, and sorry, I forgot to assign the composition. So then if you forgot to assign the composition, you can go to edit. Okay, you can choose this layer, and the material is indium gallium nitride, and we can change the composition. And for here, we say composition is 0.2. Okay, we can say it's 0.2. Then we can apply it. Then you can find the composition is changed. Okay, so we can refresh the structure by here. Okay, let's put it full screen, and then we can refresh the structure. Okay, so this is indium gallium nitride content wires here. Then we can add another layer. Okay, so what's the thickness of another 100 nanometer N-type? So we can say 100 nanometer is 1000 angstrom, and it's N-type. So we say the doping is 5e18. Okay, we can say doping is 5e18. Then we can apply. Then, as you can see, we have a gallium nitride, indium gallium nitride, and the gallium nitride quantum well. Okay, so this is the design of epi-layer. You can find it very fast. So now you can see all the material parameters here. You can find the effective mass, dielectric constant, everything is assigned. Then typically you have a lifetime, and your spontaneous polarization and the piezoelectric polarization. And this polarization is very special for nitride material, and we'll not discuss too much here. But then for nitride, you will always need to consider the piezo polarization. And you can see there's a polarization button here. And this is the electron affinity. So you can decide the heterojunction by electron affinity or not. So, but you can tune this, but this usually is using the default parameters. Then try to run this program. There's a panel here. You can see the context setting. Okay, for context setting, that's the top is the BIOS point. So the BIOS is always on the top. And you can choose the BIOS range. So, for example, we can start from 2 to 4 volts, and the step is 0.1 volt. Okay. So after this, you can set a max step, and this is P-type and N-type. So this is ohmic contact. So we can say the doping is decided by dope. But if you want to make a Schottky barrier, then you don't need to use that. You can assign a Schottky barrier. Okay, you choose this, then you decide what's the DZ for the simulation and the temperature. You press OK, then the structure is ready for the simulation. Then you can set up run the simulation program, and set up the context setting. It will ask you again, click OK, and save. After you save, you can find the simulation program is running. For 1D, the simulation is faster, so you can find it run very fast. And okay, then after finish the simulation, okay, you can see it's finished. Then you can go into the result section. Okay, you can find, also you can run a lot of different tasks. So you can go into the result section and you can see here. Okay, this is the result section. Choose your project test 1, and you can find you run from 2 volt to 4 volt. Okay, you can see this. And then what you can plot first is the Venn diagram. So for the Venn diagram, what you can plot is something like this. Okay, if you want to plot EC, EFN, EV, EFP, you can pre-choose. And then you can plot like N and P. This is a electron and the hole density. And you can plot JN, JP. Okay, there's no current. And if you go into 3 volt, then you can see the current. Okay, you can see the current density. Okay, then this is for different voltage, but you can also plot the IV curve. So IV curve that you can see, you can choose different axes. So the first axis is the voltage, and the second axis is the current. That means the current flows from the top, and the right current is current from the bottom. Then you can see the current density. Okay, this is the IV curve. Okay, you can also plot the log scale. So you can find that we start to have current at near 3 volt. So this is the IV, and you can see the IQE curve. So for the IQE curve, you can choose. Okay, if you don't want to click log, then you can plot IQE. Okay, so you apply the IQE versus voltage. So you can see this. Then of course you can choose the x-axis is the left current. Okay, then you can plot the IQE versus the current. Okay, you can choose this to be Y1. Okay, you can find that this curve is very strange. It's because this current density is too large. So you can make it a scale. You can scale it down. Okay, you can scale it down. Then you can see, oh, this is a traditional IV curve. But because our delta V is too large, so you see this curve is very ugly. Okay, so if you want to improve this, it looks like we only need to run 3 volts. So if you look at IV, okay, if we get a IV curve, okay, we can find that we only need to go into the 3.2 volt. It's something like in this range. So we can rerun the program from 2.5 to 3.2. So if we go back to run the simulation again, so we can run, let's say, okay, I want to change the BIOS from 3.4 to 3.2. And the delta V, we can set up it to be a smaller. Okay, then we can run the program now again. Yes. Okay, save. Okay, now you can see it's running with the smaller BIOS. So if you go into look at the data, then you can press refresh. Okay, so after you click refresh, you can open the program again, and you can see there are different data here: 2.51, 2.52, 2.53. So you'll see more data, and if you look at IV curve, you can find it becomes more smooth. That's because you choose a smaller delta V, so you get better IV in the simulation. Okay, then if you look at the IQE curve again, so we can say if we say IQE versus left current, then you can find it becomes much more smooth. Okay, and then we can refresh. After you finish, you can refresh it again. And if you look at IV, IQE, then you can find this is a typical IQE curve. And for the interface, you can find, okay, this is the IQE curve. Then there are more settings in the result section. Okay, so for example, if you want to see the band diagram, okay, you can always choose your voltage range. For example, if you have 2.7 volts, this is the band structure, and you can find that this is the quantum well. Quantum well is here. Okay, you can plot the N and the P on different axes. Okay, so if you look at this, okay, you can find this is the electron and the hole density. Because nitride they have a piezoelectric polarization, so you will see a very clear band bending and the carrier accumulate on either left-hand side or right-hand side. So this is a band structure. Okay, so of course that you can plot the current. So we already use this, so we can choose don't plot N and P, and we plot Jn and Jp. So you can find electron and the hole, basically electron current flows in and the hole current flows in, and they are recombined in the quantum well. So you can see this. Okay. All right. So after this band structural simulation, then we can make comparison. For example, if we're going back to again to the default setting, we say this is for 2.7 volts. So how can I compare to 2.8 volts? So we can go into project, and the project test, I can choose 2.8 volts. And we can go into the band diagram, and I can choose is this one, and click the left button, move to here, then it will plot the 2.8 volts together, and then you can make comparison here. Okay, but if you want to put carrier density N and P in, then the most important is that you need to, because this is EV, so you have a different unit. So the most important is that you click the right button. Okay, you click the right button, then you move it in. So if you click the right button, then you can see that you will use the right axis. If you click the left button, you will use left axis. So you can click this in, and you can see the electron and the hole plot. Okay, so this is a hole density. This is electron density, and this is the hole density. So you can compare the data for different bias. Then if you go into here, then you can see this is the raw data for EC, EV, EF, and EFP. Okay, if you go into like 2.85 volts, then you will see this raw data. So if you choose different data set, then the raw data will be here, and you can make a copy, Control C, and if you have Excel, okay, if you have Excel, then you can copy path, use Control C and Control V, you can copy path to here. Okay, so you can do the later processing of the data if you want to do it manually. Okay, so that's how to use the basic interface. Okay, right now we already finished the simulate PIN diode structure with the quantum well. So in this solver, in this part we simply solve Poisson and drift-diffusion equation. Okay, so if you want to solve the Poisson drift-diffusion equation in this PIN junction, then basically we are treat the particles in the quantum well is just like a classical particles. So it's decided by the 3D density of state, and it's not really considered a quantum Wells problem. Okay, so carrier will be confined, but it's just not like wave. It's just like particles. So you will accumulate you can see the carrier accumulate on the sidewall very clearly. So if you look at the result, okay, for project 1, if you look at the carrier density, okay, at the turn-on BIOS, okay, you can find that the carrier density simply just like a particle that accumulates at the sidewall. Okay, the sidewall is part. It doesn't look like a wave. Okay, so to simulate this kind of structure, that you can solve the Schrödinger equation. So there are 2 models in the program to handle the quantum condition. First is using the localization landscape theory, that it will help us to solve the effective quantum potential. The second is that we can solve the Schrödinger equation to get the solution. But the best way is to solve both together. So we can solve potential landscape, self-consistent, and you can even include the light hole band. Then you can decide if you want to calculate PL or EL, and then you can decide to solve Schrödinger equation. For solving the Schrödinger equation, you need to set up the active region. So for the quantum well, this red color is the active region. So we can set up the active region just as if I change it to this number, okay, make it refresh, we can say there is a region that will solve Schrödinger equation. Because for eigensolver, in the later class, I will teach that for eigensolver, you will require more memory. So the mesh size is better to be not as large as the traditional Poisson drift-diffusion solver, because they only solve the inverse. But right now, if you want to solve eigenvalue problem, it's possible that it's a full matrix. So you need to set up a region, active region, to solve Schrödinger equation. So you need to choose a proper region, maybe 900 to 1030, 1130. Okay. Typically, because wave will a little bit leak out to the quantum well, so we can not choose just the quantum well region. We need to set up a proper region, and then we can decide it. Okay. So there's another function to help you to decide. Just tell him which layer is the active region. For example, if you say this, so the program will help you to decide an active region. But typically, the result is the same. Okay. So you enable a localization landscape theory, you will get effective quantum potential, and you can try to solve the solution self-consistently. So after finish the setting of solving Schrödinger equation, calculate EL, PL, we can save as project test 2. Okay. Then after this, then we can try to solve it. Just click run. Yes. And the content is the same. Applied voltage range is the same. And we save. Okay. So after you solve this, maybe wait a few seconds, you can get a solution. Okay. So when program is trying to solving the Poisson drift-diffusion equation, we can go to look at the result first. So this is project 2, okay? So if we go to project 2, okay, then let's make it larger. So some BIOS is already solved. For example, 2.7. If you look at the signal, we can find it's already solving 3.1 volt. So we can say, okay, for This is old project. Okay, for project test 2, this is the potential. Then if you look at the carrier density now, okay, Y2, and you can look at carrier density Y2. Okay. And you zoom in, you can find that the particle doesn't look like to be the same as the traditional particle. So if you compare this to the project 1, okay, at 2.7 volts, okay, you press and use the right button and the P with the right button, okay, you can find that except the carrier density is quite different, the shape is different. This is more like wave function, and this is more like a particle. So there is a peak shape here, but this is behave more like wave. So if we compare electron and hole, then you can find that this is a difference, and there is some leakage of a wave outside to the quantum well. So that's the difference for electron. Okay, and for holes it's similar. There are some holes more extended outside to the quantum well. So if we go to the wave function, okay, we can say go into the Venn diagram, and if we go to the electron wave at 2.7 volt, this is the first eigenstate, and we have only one state. And for whole wave, we have 5 states. Okay, we have different whole wave. Okay, so you may think that how the whole wave distribution compared to the quantum well. So the way to see this is that we can see the electron Fermi level here, and again going to the project. Okay, this is not project 1, this is project 2, 2.7 volt. Choose here electron wave, and you can move this in. This is the first eigenwave, and this is the whole wave. You can move it in. Okay, this is the first whole wave. This is the second whole wave. This is third. This is the third eigenstate. Okay, so we have different eigenstate here. This is a wave function. Okay, you can see electron wave is more like this. Okay, this is not carrier density. This is just the wave function format. Okay, then if you compare this wave function to the carrier density, then okay, we can go back to the band structure, press N right button. Okay, then if you look at this, they say that this is the electron wave, and there is a discontinuity here. This is due to the quantum well. Carrier density is something like this. And the same for holes. This is the first whole wave, and if I put holes, right buttons in, okay, then I need to change the scale. You can find that the extension of holes, okay, compared to the holes, we need to change the scale. But anyway, we can change the scale by, okay, we can tune the figure. Sorry, should be something like this, and choose Y2. Okay, and we can choose the Y range to be larger, maybe to 19, right? Okay, and then maybe 20, so the carrier density is too high. Okay, then we can compare. This is the whole wave. If you want to normalize to a more close scale, maybe we change the scale again. 5. Okay, you can compare these two. It's more like a wave function shape of the whole wave. So this is how to solve the band structure, and you can look at IV. This is a new IV curve. Okay, And I think we already finished the simulation. So we can refresh the data, okay, and replot again. And you can find it's going to 3.2, which is the end voltage. So we can look at the IQE curve. So this is the IQE curve for project test 1 and project test 2. Sorry. Okay, you can see it's more sharp for project test 2. So if we try to compare both, okay, we can say that, okay, this is IV, and if we say this is IQE, okay, this is the IV curve, and this is the difference. So the quantum model has a better electron hole overlap. So the droop is much less strong compared to the traditional model. So this is the quantum model. This is the project 1, the previous model. And the IQE behavior is different. So this is considering the quantum effect. This one does not consider quantum effect. So how about the band structure? So if we compare the band structure, this is a traditional EC-EV for project 2. We didn't see much difference, but the difference is here is that we can solve the effective quantum potential. So if you look at the effective quantum potential and compare, you can find that the real quantum potential seen by electron actually is more like there's a confinement here. So carrier cannot go into any potential lower than this, but there is a little bit tunneling effect. Like carrier can go through this barrier, and you don't see this tunneling barrier. So carrier is more easy to leak out or leak to the barrier material. So that's a difference. Okay. So if we compare this, then this purple line is the effective quantum potential, and the blue line is the real EC. So with this model, we can include a quantum effect into the simulation. I know that some program, just like some student asked me in the class, is that some software will say they can separate domain. So they solve Schrödinger equation in this box, and they try to connect the outside domain into the middle domain, and they try to connect each other. But with this method, there are some very tricky point, is that how can you connect two domains without any problem? Because you have some place to cut off and decide this is the box inside and the other is the box outside. So you need to make a transition between a box inside and outside. So the software will be more unstable. So with the localization landscape theory, it's possible to do this. Furthermore, we can calculate the emission spectrum. So in this case, 2.7 volt, okay, we can find that this is the EL/PL versus gap and lambda. So if you want to see the emission wavelength, in this case, it's 480. Of course, I can compare two different bias. So if I go into project 2 to 2.9 volt emission spectrum and EL/PL click in. Okay, it's in different scale. So I can change the scale. Sorry. I can change the scale bar to be a larger range. Okay, so this is the emission spectrum. Okay, so you can find this is a peak point and this is a peak point. Okay, there's difference in the peak point. Okay, then we can look at raw data for this case. Okay, the peak. If you look at the raw data, you can see the peak is appear. Okay, the peak is near here. So in the raw data, I can find that the peak is around 481. Okay, this is for 2.7 volt, 481. And this one is a new curve. I can go into 2.9. Okay. And I look at the grid, PL, emission spectrum, EL versus lambda. Okay. And if I go into that, we can find the peak. The peak is near 479. So you have a 2 nanometer wavelength shift. That's called the blue shift of the wavelength from 2.9 volt to 2.7 volt to 2.9 volt. So with 1D program, you can calculate the emission spectrum, the electron hole wave overlap. The overlap. This color means the degree of overlap, and this is the first electron state to the second, third, fourth, fifth, sixth of the overlap of the electron hole wave. Okay, so that's the simulation program. So in here that we finished the first trial is a simple PIN diode case. So actually this program can do something more. First is that, of course, we are not limited in just simply PN diodes. We can make the structure more complicated. Okay, for example, like this is a 6 quantum well PIN LED. And there is a multiple quantum well inside. Okay, so if we try to solve this problem, okay, we can open a new project. So we can get a new project, okay, and this project could be a test 3. Okay, so I can save file savers and test 3. So this is a project 3, and we can say this is a multiple quantum well. So multiple quantum well means you have different quantum well number, the p-type doping, n-type doping there, and the quantum well, and all with different kind of setting. Okay, so how could we do that? First is that this is T and argon and gain nitride in gain, gain nitride in gain, gain nitride in gain. Okay, so the first layer we are going to add is 1 and 150 nanometers. So we say 1050 in gain, and it's n-type, it's p-type, and it's 2e. What's the doping density we put? Okay, this is full ionized, sorry, this case, 2E19, okay, so it's 2E19, and we can apply. So this is the first gain nitride layer, and we have aluminum gain nitride layer, and this is 30 nanometer, so we can put just 300 angstrom. And it's p-type, and the composition here is 10%. So we can say F composition is 0.1, p-type, default activation energy applied. So we have another p layer, so we want to put additional a layer. Okay, so what can we do? The other one is that we can put another InGaN, and I think it's 10 nanometer. Okay, 10 nanometer. Barrier between quantum is 10 nanometer. So we can put 10 nanometer, and the composition is 0. And the first layer, this is p-type, so it's still p-type. Okay, this is still p-type. Okay, so we put p-type. Gallium nitride p-type. Then we need to put a quantum well layer, and quantum layer is 70%, 6 quantum well. So we have first quantum well is 30 nanometer, and the composition is 0.17, and this is N-type intrinsic doping 1E17. So we can apply this. Okay, this is a quantum well. Okay, then we can put 100 and 0 and apply another layer. So this is well barrier. Okay, any problem? So there is something that you can do, is that this tool is decided, so I can add another layer. We say it's this. We can directly add 2 layers. Okay, so you can find these 2 layers. This is not quantum well. This is gallium nitride. So you can simply copy Control C and Control V. Okay, there is some. Okay, you cannot directly copy, and you can directly insert. Copy. Then you can insert here, and it says how many iterations. Of course, 1. So I insert layer here. Okay. I can also do the deletion. So I can delete. This is remove. So I can get 2 quantum well. So I can also choose 2 layers, and I press copy, and then I can put here to insert, and I want the 4 quantum wells, so I insert for loop. So you can find that I directly copy this quantum well pair into additional for loop. So we have 4 quantum wells. So you need to optimize this setting here, and also you can make a modification. For example, you can make a modification here. This is layer 8. Then you can say, sorry, this is not indium gallium nitride, it's aluminum gallium nitride. So if you change it, you can find this material is already changed. But of course that this is indium gallium nitride, then we can apply and then change back. So this is a total quantum well. And after this setting of 6 quantum well, finally we have N-type layer. So we have an N-type layer, and this N-type layer is 5E18, and it's 200 nanometers, so we say 2000 angstrom. 5 layer N-type, and just 1 layer. Okay, apply. Okay, so we have the quantum well layer, P-GaN layer, quantum well layer in here, and usually in the left quantum well, I can also directly modify the doping here, and just remember to refresh the data. So you can make sure that the doping is right. So you can check the doping. Okay, this is the doping concentration, and you can check the activation energy, you can check the band structure, and you can check the composition. Okay, so looks like everything is right. Then this is the content. So ideally this software is solved. Then we go into the Schrödinger software. We say that it's better to include the quantum effect. So I solve Poisson drift-diffusion. And but if you want to solve Schrödinger equation, you can find the active region is wrong. So I can set up the active region. So I set up which one is the quantum the active region. And the program will help me to decide. Okay. The program will help me to decide the active region if you choose which region number is the active region. So I can say I also want to solve Schrödinger equation. Alright, so this is the way that set up the solver. And if everything looks like right, I can start to solve the program decided by dot, and the voltage here, let's say 2.8 volt to 4 volt, delta V is this. Okay. Then we can run, click yes, run the program instead. Alright, so ideally you will start to solve the program. So typically, after solving the first BIOS, okay, this is a project test tree. So you can find this is the first quantum wave structure we are going to model. Okay, this is at 2.8 volts. You can find the whole has difficulty to reach the bottom of quantum wave because this is a gain nitride case. So this is the best structure, and you can look at the IV project test tree. The current is quite low. Okay, you can refresh the data, look at the new IV, and you can say right now it's going to 3.6. So you can find the current density is quite low. It's because for perfect quantum wave structure like this, this piezo barrier is too high, so the carrier is very hard to tunnel through this. Ideally, it's very hard to tunnel through this barrier. So basically, to solve this current issue, that we must know that gain nitride has a composition fluctuation. So this potential actually will be vibrate. Also, there might be some defect, dislocation that will help carrier to go through this tail state. So the actual voltage will be lower. So we need to tune the setting to make it more accurate. So this is just the IV curve, and if you look at 3.5 volt, and if you're going to see the wave function, and you can say, okay, I made a mistake, but that's fine. I didn't set up the project directory. Working directory. Okay, anyway. So if I look at this band structure, this is the electron wave. I can click it. Sorry, I have more quantum with 3.5 volt. I need to put here electron wave. So this is the first electron state, second electron state, and maybe the fifth electron state, and the ninth electron state, 7. Okay, you can find different electron state in this location. You can also plot the whole wave function. Okay, then you can go back to the electron and the hole density. So EC, EV. Okay, and let's say NP as a Y2. Okay, so this is the electron wave, and this is Hall wave. At 3.5 volt, you can find that Hall cannot reach the bottom. Also, electron is very hard to reach the top. So, if we look at the radiation pattern, you can find that majorly the recombination is in the first quantum well. So this is the recombination zone. Okay, so that's the difference. Okay, so when I solve the project test 3, where I have multiple quantum well, if you look at the IV curve, you can find after finishing the simulation, the current density is still quite low. As I mentioned, that it's possible that the carrier IV cannot be fit simply because the potential fluctuation as well as the possible leakage path. So in order to make the simulation more accurate, we need to tune the simulation. So the typical way is that we assume that there is a fluctuation or some leakage path. So it's equivalent that it has a lot of band structure in the intermediate state. So we can apply this function we call the density of state theory. So in the density of state theory, if you go into my website, there is an explanation here, and you can apply the density of state additional Gaussian tail state model. So it's called DOE-ITRI fluctuation. So what does that mean? This is a traditional band structure for our semiconductor solver, but because there is some defect or possible localized state inside the material, so that below the band edge there might be some additional state. This we can call it defect band, or we can call it tail state. So our program has additional function we call it DOE-ITRI function, and it allows us to add additional tail state below the band gap or above the band gap. So this is ET, and there are several different kinds of functions defined here. Okay, so you can go into my wiki and to check the function, please. So where is this setting? Okay, first is that we save as project 4 first. Okay, so this is a new project, but the same structure. So in order to model this accurately, this is the tail state function is here. So this one is corresponding to the band structure setting in this. So there are different types, and there's a definition here. Sorry, and this is 2D. Definition here. That means how many Gaussian tail states we want to set up. So ideally, program will have some default, but we can make some changes. Okay, we can make some changes. So we can say that in the N-type heavily doped region, don't put the density of state, and in the heavily doped region, don't put this, and in here none. Okay, we can put there's a tail state function in the quantum well and the barrier, so that we can try to model the carrier density. And of course, you can change the value. And after you change it, remember to refresh. Okay, remember to refresh. So I can enable the tail state function. So, and for different structure, it may have different defect density. So typically, default is 1:19. So I can add it, I can modify it. So for example, I can choose of name okay, I can change it NT okay to be 1E17. Then you can find I can change them at the same time. I can change it back. Okay. There are some default value, but it's always open to change because this default value may not be the best fitting to a simulation result. So that means I set up some tail state. In this wheel so the carrier can go through this. Okay, after this, we can do the simulation again. Save and run, and run, and should run. Okay, so it will take a few time to solve this, and very fast. Alright, so put a tail state function. If you look at the result, refresh the data, go into project test 4. If you look at IV, you can find at the 3-point volt, the current density is already over 10. Okay. And 2.8 volt is already have current. So I can have IV curve like this, and refresh again. I can have plot IV curve again. Okay, you can see there's a normal IV curve, a log scale. Okay, you can get a turn on, here. Okay, we get a turn on current at 2.8 volt, and then we have going to 3-point volt, you have 100 amp per centimeter square. So after this setting, we can get more accurate current density. Alright, so you can look at the electron wave band structure. So remember that this is a project 4, and we can have I didn't solve the PL. Okay, so we can go back to the Schrödinger. Okay, just remember that we can solve EL, PL, and of course you can solve it again. Yes. Then you will override the old data, so you can solve the simulation again. The other one is not finished, so let me close it again. Okay, so this is a density of state model. It enables us to make accurate IV curve fitting to the quantum wave LED.